speaker here, Michal Štolba and Antonín Komenda. Well, the paper is by them. Relaxation Heuristics for Multiagent Planning.
Okay, thank you very much. Okay, so I will be talking about heuristics for multi-agent planning. So first of all, I will give some introduction on what do we mean by multi-agent planning, and then I will give some more background. I will proceed with the main contribution of the paper and conclude with some evaluations and future work. So maybe unlike many other people here, we consider multi-agent planning as agents planning by themselves, for themselves, but in a deterministic environment, which means that the actions are deterministic. And this is also thanks to the fact that we consider the agents to be cooperative. So there's no one doing some like evil things to them. But the planning process itself might not be deterministic. And we are considered in the plan synthesis and coordination of the agent plans. So the main research question we were asking was if we can somehow improve the multi-agent planning by some use of global heuristic, to try somehow to compute global heuristic and use this in the search or in the planning. So the approach we took was that we took some existing single-agent heuristics, in particular relaxation heuristics, which are well known. Then we tried to share some information among the agents to obtain the global heuristic estimate, but still we want somehow to preserve the privacy. We don't want to disclose all the internal things of the agents. And then we compared it with the approaches where we do not share the information. So the actual formalism we use for multi-agent planning is multi-agent strips, which was introduced by Ronen Brafman and Carmel Domschlag in 2008. And what I really like about this formalism is that as strips is like the most common, most basic sub-formalism of most planning formalisms, the multi-agent strips follows this idea and tries to extend it with the most simple or most basic idea of multi-agent systems, which is the notion of separation of public and internal or private knowledge. In fact, I will maybe interchange those two words, but maybe internal is better suited for our approach. Okay, so the multi-agent strips problem is pretty much the same as strips problem. The only difference is that instead of a set of actions, we have a set of agents, and each agent is represented by a set of actions the agent can perform. And this is actually quite nice, because then we can separate which parts of the problem are interesting for each of the agents, and on which parts of the problem, or the facts actually, the agents need to interact. So based on this, we can separate the facts to internal facts and public facts. So internal facts are those which are exclusive to some agent alpha or one of the agents, which means that they are not used by any actions of other agents. And public facts, on the other hand, are those which are not internal. So it means that if a fact is used by at least two agents, then it's public. Similarly, actions. Internal actions are those which use only the facts of the single agent, and public are the rest. Okay, so there are two more things. We treat all goals as public, which is kind of a simplification, but we stick to this for now. And also, as I already mentioned, public means public to all. So if a fact is public, then it's public to all agents. Another important thing or I will be talking about are the projections. So a projected state is a state which is like the global state, which is restricted just to facts of a single agent. And something similar applies to actions. If we have agent alpha, but some agent beta, let's say, which have some public actions, then we can project the public actions of agent beta to agent alpha. So the part of the action which can be understood by both agents or by all agents. So we just restrict the preconditions, add effects, and delete effects to the effects of agent alpha. Okay, so the actual algorithm we are using for the multi-agent planning is some kind of multi-agent best-first search, which is just a standard best-first search with modification based on multi-agent distributed A* by Ross Nissim and Roland Brafman. And the way how it works is basically this. All agents start to search in parallel using only their own actions. But what may happen is that some of the action which is used is public, and therefore the agent needs somehow to inform that the action he's taking may affect the other agents. So it's done by sending the resulting state to other agents. And the other agents can then add the projection of the state to their open list. And if it happens that the state is good enough, it's expanded as normally, and the search continues. So this is the way how we construct the single agent plans, and also how the coordination is done. So one last information about some background information is about heuristics. I guess that you all know relaxation heuristics or delete relaxation heuristics, where we just ignore all delete effects. So it's the same. Typically, they're represented by relaxed planning graphs, but in fact, they are just the way how to see like relaxed reachability analysis or exploration. So the examples of such heuristics we are concerning are the additive heuristic, where all the preconditions must be achieved independently. Maximum heuristic, where we assume that just the most expensive heuristic is sufficient to achieve. And fast-forward heuristic, that the relaxed plan is explicitly constructed and its cost is used as the heuristic. Okay, so as I said, the way how those heuristics are computed typically is some way of relaxed reachability analysis, which is typically done by some kind of exploration queue algorithm, for example, in the fast downward planning system. So the algorithm works by first putting all the state or all the facts in the initial state into the exploration queue, which means they are reachable. And then there's some kind of loop, which ends if the goal is reached, which means that we have the heuristic, or if the exploration queue is empty, which means that we have a dead end. So in the loop, when some fact is reachable, we can update heuristic estimates of all actions which are depending on this fact. And if an action is reachable, which means that all its preconditions are reachable, we can add its effect to the exploration queue, which means that the effect is reachable, and compute the heuristic estimate of the effect by adding the heuristic estimate of the action and its cost. Okay, so now what we do is that we are trying to do the heuristics for multi-agent planning. So far, in most cases, some kind of projected heuristics were used, which means that we use just a local problem of the agent with the projected actions of other agents, which are necessary in order to reach the global goal. And this approach is prevalent in the literature. What we are trying to do is, as I said, is to compute some distributed estimate of the heuristic, but still preserve the private knowledge. So we do this by distributing the exploration queue algorithm. So how this works? We start with the original exploration queue algorithm with the agent's action and the projected actions. And what may happen is that the agent actually wants to apply a projected action, which is not his action, and therefore he doesn't really know the exact cost of the action, because it might have some private preconditions and stuff like that. So what he does is that instead of applying the action, he sends a request to the owner of the action, saying something like, hey, okay, I have this action and I need to know its precise cost. So the agent beta, which receives this request, computes the heuristic estimate from the given state, which is the states for which we are computing the heuristic, and to the preconditions of the action. So he doesn't need to compute it to the goal of the problem, but just the preconditions of this action. And when it's finished, he just sends a reply to the requesting agent, and the action can be added to the exploration queue with the precise cost, and it's all fine. But what may happen is that the agent beta, again, uses some other agents, or maybe agent alpha's action, and needs to compute its precise cost. So this results in some kind of like distributed recursion, which is not a very nice thing to work with, because it's, you need to maintain all the open contexts of the recursion. You may get some like infinite recursions and infinite loops. So the way how we cope with this is that we try to somehow flatten the recursion. And this is the way how we do it is that the agent beta doesn't send the request for this action B himself, but he includes it in the reply, saying that, okay, so this is my heuristic estimate, but I need to compute those other actions as well. So the actions are included into the reply, and the agent alpha, when it receives the reply with those actions, first sends requests to the owners of these actions and receives the replies. And after that, he can finally add the original action A to the exploration queue. This may, again, there may be more requests coming, but this is not a recursion, but this is just like nesting of this requests and replies. So it's much easier to cope with it. Okay, so there's another thing we have considered. So far we have seen projected heuristic, we have some kind of distributed heuristic, and like, is there something in between? And yes, of course, there is. For example, what we can do is that we can actually augment the messages, the requests and replies, with the current recursion depth. So it means like how deep in the recursion tree we are. And we can limit that we, at some point, we won't send any more requests. So if we are below the limit, we send requests normally and compute the distributed heuristic. But if we are above the limit, we do not send them, and we behave like if it was the projected heuristic. So this is some kind of relaxation of the interaction among the agents. And in fact, it's also a generalization of the previous approaches. So if we set this limit to 0, we get the projected heuristic. If we set it to infinity, we get the distributed one. Okay, so now results of what we have. So we have tested this approach on the fast-forward heuristic, additive heuristic, and maximum heuristic. Here we have the different settings of the recursion limit. So those are the projected heuristics, those are distributed ones, and this is something in between. We have some like domains here: rovers, satellites, logistic. This is a cooperative pathfinding, which is a like multi-agent domain based on quite famous multi-robotic problem of robots moving on grid, and Sokoban. And what is maybe the most important observation in this table is that the distributed heuristics actually help in the results, which are like the IPC score in terms of time. Another table is a coverage. So we have some about, I think, 40 multi-agent problems, and I think there was maybe 20 or so IPC problems. So the multi-agent problems are in fact as well based on IPC domains, but there is typically more agents, and there is less they are less combinatorically hard. Here we can observe the same pattern, that the distributed heuristic is actually better. But what is interesting here is that we have like different numbers for the recursion depth. And what we can observe is that it doesn't really make much difference. So this is because that on most of the domains we have used here, the actual maximum recursion depth we can reach is somewhere between 1 and 2. So it actually doesn't make much difference to limit the recursion depth. It can be a little bit better seen in this graph, where we have here are the different limits of recursion depth, and here are the times, but they are normalized against the distributed heuristic, against infinite recursion depth. So this is this line, and whatever is above is slower, and whatever is below is faster. So here we have rovers and satellite problems, which are pretty much loosely coupled. There is not much interaction among the agents. And we can see that actually the projected heuristic here doesn't perform very well. And that is because there's a lot of private information. And therefore, if we use this information, we get much better results. On the other hand, the cooperative pathfinding, as I said, most of the information there is public. All the actions are public. And what we can observe here is that actually the projected heuristic performs better than the distributed one. And we can also see that as the limit grows, the performance gets worse. So this is because most of the information, as I said, is public, and therefore there is no need to share any of the information. Basically, that gets me to the conclusions of the paper, and that is that the use of distributed heuristic actually can improve the performance of a multi-agent forward-chaining space-based planner. That's what we have used. But more precisely, what we have observed is that the projected heuristics are actually quite good for very coupled problems. So if there is a lot of a lot of public information, most of the information is public, there is really no need to compute the distributed heuristic. And also the communication overhead is really significant because there's a lot of other agents' actions we need to request. But on the other hand, the distributed heuristics are quite good for loosely coupled problems because there's a lot of private information which we are missing if we do not compute the distributed heuristic. And the communication overhead there is not so crucial because there's not so many public actions we need to ask about. So about some future work or things we are working on right now is actually we are trying ways how to combine the projected and distributed heuristics in order to combine their benefits and mitigate their negative effects. So far, in fact, the limited recursion depth was one of the attempts, but as you have seen, it too quickly converges to the distributed heuristic. Another things we are trying is some kind of multi-heuristic search, but like the most naive or approaches which are in the literature doesn't really work, because in this case it converges to the projected heuristic because it's much faster to compute it. And that's basically it. So thank you for your attention, and if you have any questions.
Okay, we have time for a few questions.
Well, just a brief question, because maybe I've missed it. But in the case you have two agents that have a public action you need for a precondition, you will ask your estimates to both of these agents. And in the case you have both an action from yourself and from another agent, you will also ask his estimates, or you will only use your own estimate?
I'm not sure if I got the question. So you mean like joint actions, or?
No, no.
You mean like in the recursion kind of thing, if you get...
When you ask an estimate,
yeah.
You ask all of the agents that can achieve that.
The preconditions.
Yeah. Or just one.
No. What you do is that you ask about the action itself. So the action is owned by one agent. Yeah. So you ask the owner of the action, and the thing with the preconditions is that the owner actually computes the plan to the preconditions. So it doesn't have to compute the whole relaxed plan or whatever. So.
Another question from Stefan over there.
This is just a short one about Sokoban, because that was, when it was published, first some results, it was actually entitled Single Agent Search Challenge. So
okay.
how does multi-agent Sokoban works?
Okay, I think it's just simply adding more players there, so they are like pushing all the boxes, and so there is also most of the information is public there, because you can affect all the agents by pushing the boxes, and you also need to avoid other agents, so you're not getting stuck. So it's nothing.
So there's no privacy issue in there.
I don't think there is much privacy there. Yeah.
Yes, right here.
So you talked about your strategy for turning the recursion into sort of iteration by, it looked like you were saying, here's my estimate, but add in this, whatever the cost for this action is. Is that right?
Yeah.
How does that work if that changes the critical path when you're doing something like HMax?
Yeah, the approach here wasn't aimed at computing the exact heuristic which would be computed in the global problem. We had this topic in paper last year, which was quite nice to compute the exact estimate, but it was really not efficient because a lot of things. So here we are not trying to compute the exact estimate. So we are just adding the results of the other agents' costs. So it doesn't make the same estimate. It would be possible somehow to send the part of the graph and then to compute the actual things that affect the cost of the action, but we do not do that. No,
You'd probably also lose all of the privacy ideas.
Yeah, you would need to do it very carefully in order to.
So that means that in this example,
so
HMax, when you distribute it, is no longer
yeah,
admissible.
yeah.
Okay, thank you.
Okay, thanks again.